This recording explains how to work certain Hardy-Weinberg equilibrium problems. Okay, so in this problem, a human population of 1,000 people, 840 are tongue rollers, and they tell you that's big T or big T, little t, and 160 are non-tongue rollers, little t, little t. What is the frequency of the dominant allele in the population? So the first thing to look at is what these numbers represent. So remember our equations, so we have P plus Q equals 1, and really what that means is that P is the frequency of the big A allele, and the Q is the frequency of the little A allele. Then we have P squared plus 2PQ plus Q squared equals 1. And really what this means is that I'll put F for frequency, the frequency of big A, the frequency of big A, and the frequency of little a, little a. So those are what we use for working all the problems. Alright, so they tell us that the population is 1,000 and 840 are tongue rollers. So 840 out of 1,000 equals 0.84. So 0.84 is the frequency of tongue rollers. Now the thing here that they tell you that that's both big T and big T, little t. So if you look here at our equation, big T is like this, and big T, little t is like that. So really 0.84 is all this part of the equation. So that actually equals your P squared plus 2PQ. And just what this means to me is that you can't do much with this right now because solving for 0.84 equals P squared plus 2PQ is difficult. So what else do we have? We have 160 non-tongue rollers equals 0.16 as the frequency, and that is the frequency of the little a, which is Q squared. Now that's easy to solve for. Because really, what are they asking us for? The frequency of the dominant allele. So they want to know what's the frequency of big T. And if we look here, that's going to be this term, so P. So I'll remind myself that's what they're asking us for, the frequency of big T, which is P. So to solve for P, well, I'm going to solve for Q first because that's easy. So what I'll do is I'll take the square root of 0.16 equals Q, because if you take the square root of Q squared, that equals Q, and then you take the square root of the other side as well. So that's going to say 0.4 equals Q. If we go back, P plus Q equals 1. And the way you could think of this as well is saying, well, 40% of the population, or 40% of the gene pool is Q, meaning little a, or little t. So what's the rest of the gene pool? That must mean 0.6 is the frequency of big T. And that's what they're asking us for. They're asking us for what is P, and so P equals 0.6. So if you looked at all the alleles in the population, in the gene pool, you'd find that 60% of them were big T alleles. And some of those would have come from the homozygous dominant, and some of those would come from the heterozygote. Okay, here's the next problem. In a population at genetic equilibrium, the frequency of allele big A is 0.5. What is the frequency of the homozygous dominant genotype, heterozygous, and homozygous recessive? All right, so let's look at what they're asking us for. Remember our P squared plus 2PQ plus Q squared equals 1. That's the genotype frequencies. And P plus Q equals 1. That's the allele frequencies. They're asking us to solve for the homozygous dominant genotype, which is going to be this term here. So we're looking for what is P squared. We're looking for heterozygote, so we're looking for 2PQ. And we're looking for q squared. So basically, this entire equation is what we're trying to solve for all the different parts of that. So what do they tell us? The frequency of the big A allele is 0.5. So what does that mean? So the frequency of the big A is P, so P equals 0.5, which means that Q equals 0.5, because P plus Q equals 1. So if we put that into the equation, we'll just plug in P's. So P squared equals 0.5 squared equals 0.25. So that's one thing. That's the frequency of the homozygous dominant. We can do Q squared, which equals also 0.5 squared. So 0.25 is the frequency of the homozygous recessive. And really, we should write that in there as well. And then we have 2PQ. So that's 2 times 0.5 times 0.5 is going to equal 0.5, and that's the frequency of the heterozygote, big A, little a. And so then we've solved for all they're asking us for. All right, here's the next problem. Suppose tallness is a dominant trait. If 96% of the garden peas in a population are at genetic equilibrium are tall, what is the frequency of the dominant allele? So, tallness is dominant, and so tallness is coded for by a genotype. So that means we're looking at genotypes. So tallness incorporates, and this is the key, both these two terms. They're going to look tall, the ones they represent. So AA and big A, little a, both look tall. So the frequency here, 96%, 0.96, equals P squared plus 2PQ. So we can't do much with that. But what we can do is the non-tall plants, the short plants, the frequency of those. So that must mean the frequency of the short plants is everything else, the rest from 96, so that's 0.04. So 4% of the population is short. And this is what we're really going to use here. So we take the square root to find Q. So Q equals the square root of 0.04, and that's going to equal 0.2. So that's frequency of the little a allele, and they're asking us for the frequency of the dominant allele. So that means we're looking for P, and P equals, or P plus Q equals 1. So P is going to equal 0.8. So the frequency of the big A allele is 0.8. If 16% of the individuals in a population are homozygous recessive, what is the frequency of the heterozygotes in the population? Okay, so homozygous recessive is represented by Q squared. This is a genotype, so it's little a, which is Q squared. So we can write that down. So that's what they're giving us. Q squared equals 0.16. And remember, it's the frequency, so it's the decimal. They want to know what's the frequency of heterozygotes. So heterozygotes are 2PQ. So 2PQ equals. So as usual, we're going to solve for Q. So we can take the square root of 6.16. That's going to equal, Q equals 0.4. And what does that mean? That means P equals the rest of it, so 0.6, because P plus Q equals 1. And then we just take those 2 times P times Q, and that's going to equal 0.48. So the frequency of heterozygotes in the population is 0.48, or I suppose you could write 48% if you really wanted to. But the frequency is usually represented by the decimals, so 0.48 is the frequency of heterozygotes. The genotype frequencies in a population, so that tells us we're looking at this, are determined to be 0.6 for big A, 0 for big A, little a, and 0.4 for little a, little a. Is this population at genetic equilibrium? Explain. So I'll show you the short estimate way to do this. There's a longer way with chi-squared involved, which I can do next, but this gives you a good idea of whether it's an equilibrium or not. Okay, so to be in equilibrium, that means that this equation and this equation must hold true. So since they give us the numbers for these terms here, I'm going to put those below it. So 0.6, 0, and 0.4 are those numbers. And so what I like to do is just to solve for P and Q and see if they fit properly into this equation. So the square root of 0.6 equals P, and the square root of 0.4 equals Q. So that means P equals 0.775 and Q equals 0.632. So P plus Q is supposed to equal 1. And if you look at that, obviously it's going to be greater than 1. So, since it's not equal to 1, that means it's not at Hardy-Weinberg equilibrium because P plus Q is not equal to 1. So, and you can kind of look and see that it was kind of weird anyway. There's no heterozygotes in the population, which is pretty unexpected considering that there's big A alleles and little A alleles, and they should be mixing at least some. So then what you do with this is you go back to your 5 characteristics that need to be in place for a population to be at Hardy-Weinberg, and you could look at those and see which one of those is being violated in the population and why for some reason do you not have any heterozygotes here. So when it does not add up to 1, that's a good estimate of whether it's in Hardy-Weinberg equilibrium or not. If you want to see the long way of working this, the really technical way, I'll do that now. All right, so I'm going to say that the population is 100. It doesn't tell me that, but it doesn't matter. I can just make it up. That's just going to allow me to see how many organisms are of each of these genotypes. So, if we're looking at if the population has these P's and Q, or P squared and Q squared, we're going to solve for what P and Q should be. And we're going to do this not with the square roots, but by looking at alleles. So the frequency of the big A allele, there's 60 of those people if it's 100. There are 0 of the little a, and 0 of the big A, little a, there's 40 of those people. So if we look at what P should be, which is the frequency of big A, that means each person here donates 2 big A's. So that's 120 big A's. And that's all there is. There are no heterozygotes. And out of all of the individuals, there are 200 alleles total because each one's diploid. So that means that what we end up getting is 0.6. Now this is a little bit of a funny example where these frequencies they give us are going to equal the frequencies of big A and little a because there are no heterozygotes to contribute more big A's or more little a's. But you'd work it the same way if you had heterozygotes. And in that case, all you would do is, let's say you had 10 heterozygotes, you'd say that for the big A's, they donate 10 big A's, and they donate 10 little a's. So you'd add that on to the number of alleles that are donated by the homozygous dominant. So it would be like 60 plus 60 plus 10. But in this case, we don't have any heterozygotes. So the frequency of the little a allele equals 40 plus 40, so 2 of those, so that's 80, and there's nothing from the heterozygote out of 200, and that should equal 0.4, which again, P plus Q equals 1, so that's what we see here. Now this is when we take our frequencies, so this is telling us what frequencies we actually have in the population. They will not always, usually they will not equal the genotype frequencies. But then we solve for how many individuals we expect to be in the population for each of these. So we expect P squared is 0.6 squared, which equals 0.36. So we expect the frequency of big A to be 0.36. And we can already see that this and this do not match up. Then we do 2PQ, and that's going to equal 0.48. So we're actually expecting 0.48 to be the frequency of the heterozygote, which we see as 0, so that's way off. And then just to finish it out, Q squared equals 0.4 squared, which is going to equal 0.16, so we expect 0.16 to be the frequency of little a, and instead we see it being 0, so that's way off. So these are the expected frequencies down here, and the real frequencies are what we see at the top. So what you do is calculate the number of individuals in the population they give you that are expected to be the different genotypes based off of these frequencies compared to the number of individuals in the population that you actually see with those genotypes, and then you do the chi-squared test. And the chi-square test is a statistical test to see if there's significant difference between the two numbers. And you can look that chi-squared test up. There's lots of examples of Hardy-Weinberg equilibrium chi-squared online. You need to just Google that or YouTube search that, and you can see. Okay, the chemical PTC tastes bitter to most people. It's a dominant trait, but is tasteless to others, a recessive trait. About 30% of Americans are PTC non-tasters and 70% are tasters. Estimate the frequency of the alleles. So what do we have? They tell us that it's a dominant trait. So to be a taster, let's just remind ourselves, that's going to mean you're big A or big A little a. And to be a non-taster, the only way to get that is little a, which is the key here. So we have, and this is Q squared, this is P squared, and this is 2PQ. Okay, so non-taster, the frequency of non-tasters is 30%, so 0.3 equals Q squared, and then 0.7 equals both P squared plus 2PQ. So we're going to solve for Q squared again, so Q equals the square root of 0.3, and that equals 0.548, or 0.55, so that's the frequency of the little a allele. I do 0.55, and then we can do that subtract from 1, so the frequency of the big A allele is 0.45, and that would be what we call P. If a population of 2,000 is at genetic equilibrium, but only contains 180 individuals with the recessive phenotype, what would you predict about the frequency of the recessive allele 9 generations later if equilibrium is maintained? So if equilibrium is maintained, we expect the allele frequency to stay the same. It's the whole thing of Hardy-Weinberg equilibrium. And so let's solve for the allele frequency so we can say what it's going to remain as. So recessive phenotype, that's 180 individuals out of 2,000. That's the frequency. And that equals 0.09. And that is actually equal to our Q squared. So Q is the square root of 0.09, which is 0.3. So we expect the frequency of the little a allele to stay at 0.3 after 9 generations if it's in Hardy-Weinberg equilibrium. If the genotype frequencies in a population are 0.36 big T, 0.48 big T, and 0.16 little t, what are the allele frequencies? So assuming this is in Hardy-Weinberg equilibrium, we can look at the little t, which is Q squared, and that equals 0.16. And so you can take the square root of that, and that's going to give you Q is equal to 0.4. Q is equal to 0.4, that means P is equal to 0.6 because P plus Q equals 1. We could also solve it like this, so we can pretend the population is 100 individuals, and so that means 36 individuals have big T, 48 are big T, little t, and 16 are little t. So we want to know the allele frequency of the big T. So that means each big T donates 2 big T alleles, and each heterozygote donates only one of those. And then in our population as a whole is 100 individuals, and so that means each of them donates 2 alleles, so that's 200 alleles total. And what that means is that we have 120 alleles out of the 200 that are big T. So the frequency of that is 0.6, so that's the equivalent of P, the frequency of big T. And then we can either do the subtraction, or you could look at these numbers. So 16 individuals donate 2 little t's, 48 donate 1 little t. Divide that by, again, 200 alleles total, because each one person donates, or one individual donates 2 alleles total. So that's 80 out of 200, and that's going to equal 0.4. So 0.4 equals Q, which is just what we found before. So there's just 2 ways to work that. The genotype frequency in a population are 0.64 big T, 0.32 big T, little t, and 0.04 little t. What are the allele frequencies? So I'm going to solve this what I think is the easiest way. So 0.04 equals Q squared, which means Q equals the square root of 0.04, which equals 0.2. So that is Q equals 0.2, and that means P equals 0.8, and that's what they're asking for. So this is the frequency of your little t, and this is the frequency of your big T allele in the population. If the frequency of allele big A in the population is 0.7, so 70% of the alleles are big A, what is the expected frequency of the carrier or heterozygous genotype? So the frequency of big A, that's going to be P equals 0.7, which means Q equals 0.3, because P plus Q equals 1. Heterozygote is 2PQ, so that's 2 times 0.7 times 0.3, and that's going to equal 0.42. So the frequency of the heterozygous genotype in the populations expect to be 0.42. That's 42%, but frequency is usually represented by the decimal. So this can be useful in populations to determine perhaps carrier status based off of the number of individuals that have the disease. If it's recessive disease, then you could actually calculate the carrier percentage of the population expected. So those are the 10 questions on this worksheet set for Hardy-Weinberg equilibrium.